Hello, good morning, good afternoon, good evening, wherever you're joining from around the world. My name's Robin Moffatt, and I'd like to show you some cool examples today of the kind of things you can build with Apache Kafka, with Go, and a tool called ksqlDB. So I'm coming to you today from the lovely county of Yorkshire. It's in the north of England. It's kind of like halfway if you draw a line between London and Scotland. It's like somewhere around there. And as you can see, it's like beautiful countryside. It's a little town nestled in a valley, and it's a lovely place to live. I'm very, very fortunate. And there's like good facilities and stuff like that, but sometimes for bigger shops and cinemas and stuff like that, we need to go to a nearby city. So in this case, we hop in the car and we go to a place called Bradford. And as one does, sat in the car, driving along, one thinks, where am I going to park the car? So we need to find a car park. So you need a car park. Well, you need to know, well, where is the nearest one that's got some spaces? Or how many spaces are there at my favorite car park? Or perhaps you can't find any car parks and you're driving around, and wouldn't it be useful to know when there's a car park comes available with some space? And being data geeks, we also want to know, like, well, how does occupancy vary over time and all those kind of things. So this is the scenario for what I'd like to show you today. I'm a developer advocate at Confluent. Confluent are one of the companies that work on the open source Apache Kafka project. I do blogging, I do tweeting. You can follow me at @armoff. I've also got a YouTube channel, so go along to that. Make sure you tick the subscribe button and the thumbs up and all the rest of those good things. So what I'm going to show you today is all driven from an open source of data published from the Northern Data Hub, and it's information about the car parks in Bradford. And it's an API that we can fetch some data from, and we're going to use a tool called Telegram to present this as a front end to our users. Telegram, it's a messaging platform. It's kind of like WhatsApp, it's like Facebook Messenger, it's like any of those things, and it's got a really good API for writing bots. So not only can you use it for chatting with people and in groups, you can also use it for writing bots that other people can interact with, and that's what we're going to do here. Let me start off by actually showing you the kind of thing that I've built, and then I'm going to walk you through bit by bit how I've put those different components together, and then we'll do some slides and talk through the kind of the architectural concept behind this and why I've put it together in the way that I have done. So let's actually have a look at how this thing works. Over here, if I can find the correct screen to share with you, which is always interesting when it disappears. It's this one over here. So on the left-hand side, it's just the debug running for my actual bot. And on the right-hand side, we've got Telegram. Telegram, you've got a desktop app, you've got a phone app, a tablet app, however you want to use it. So I'm showing you on the desktop, but you can imagine you sat in the car with your phone open while someone else is driving, and you can actually start to use this thing to interact with it. So the first thing we're going to do is we're going to start the bot, and it's hopefully going to say, I've started and I've launched. But probably being a live demo, there we go, we found the right one there. So we've got the bot and it's launched. And on the left-hand side, we can see it received a message from the user, and our user here has now got some information about the bot. Here are the different things that we can do with it. So what I can do is I can say there's a particular car park that I'm interested in. I wonder how many spaces there are available. So I'm going to say there's a car park called Broadway, and the bot's going to go off and it's going to find out based on the current information. So as of 1716, so that's BST, so GMT +1. As of this time, there's a whole bunch of spaces. There's over 1,000 spaces available in this car park, which as you can see is rather big. It's only 12% full. That's useful. We can actually do these lookups. And this information I'm showing you here is coming from that API that I told you about with Kafka and ksqlDB providing the platform for this. We might also say, well, actually, that car park, turns out it's nowhere near where we want to be, but I'd like to know where my nearest car park is. So you can say, I'm going to send it my location. So I'm going to pretend that we're driving along and we're somewhere like here, and Telegram's going to say, I'm going to let you send this point eventually over to the bot. This is okay, I've received the latitude and longitude. You can actually see in the background here, it's running a SQL, and I'll show you that SQL later on. But it's now working out, as the crow flies, which is the nearest car park closest to this particular position that has got some spaces available. So any moment now, if you like drum your fingers, you'll see, there we go, there's the answer. We've actually got this one here, which has got 107 spaces free, and it's 14 or just over 14 kilometers away. The last thing I'm going to show you is how we can actually use it to process a stream of events as they arrive. So in this case, we're going to say, I would like to receive an alert. So this event-driven notifications. I'd like to receive an alert when there becomes a car park free with, well, we saw this one here was 1,000 spaces. So that's not such a good example. But let's just say, more than 500 spaces. So I guess we're going to get this one here, Broadway, plus some of the others. It's always the challenge with using live data for your demos because you can't suitably mock it up. But it gives a nice idea of what you can do with real APIs. Okay, so we've got these ones here. We've got a couple in Leeds, which is another city nearby to Ilkley. That's got some spaces. We've got these Bradford ones here. We've got Kirkgate, NCP, and all of the spaces are over that threshold that we set of 500. So this is what we're going to build out today. I'm going to cancel the bot, otherwise it's going to keep on ticking away and sending me notifications whilst we're actually going through the demo, which is useful, but I'm not driving there at the moment, so I don't need to know. I've set up a poll on the Slido thing, so to the right of where you can see me talking. I guess if I point about here or here, depending on the mirroring, you'll actually see the poll and you can tick it if you've used ksqlDB before, and I'll switch over the poll to a different question in a bit. If you've got any questions, I'll be pausing intermittently. You can use the Slido thing, again, in that same little box up there. Turn to your questions, or if you're on the Slack group, it's room 1, and you can also enter questions there. So let's have a little look at how we've built this out. So I'm using Go. So I'm going to close down this thing here and make this a little bit bigger here. I'm using Go to write it. Learning Go has been a project of mine recently. So if you notice any like real clangers or bloopers in the code, feel free to let me know. I will be delighted to improve my Golang writing abilities. But we're going to have a little look at the code here. So we're going to say open up VS Code with this. And let me zoom in a little bit so that you can see what's going on. So this is the shell of a Telegram bot. So I'll show you the actual code for the car park one later on. But to start with, let's just look at how you integrate between Telegram itself and the bot. So how you can write that. The library we're using is this one. It's a really good library. It's very comprehensive. It's very easy to use. And when you're working with Telegram, you need to create a bot and you register with it something called the bot father, and it gives you an API token. So you set up the bot, you give it a silly name, and you get an API token which you need to configure. So the first thing we do is we provision that bot and we say we're going to create a new one, or we're going to authenticate ourselves to the Telegram service using that. Assuming that happens, we then say, I would like to receive any updates that are sent to this bot. And in the Go world, they arrive on a channel. So we can then read the messages off that channel as they arrive and handle them. And we do that using this for loop. So we simply say, here is my updates channel. I would like to process every message as and when it arrives on it. So that's what this range thing here does. It basically says, keep on processing messages as they arrive until the channel gets closed. So if the Telegram service closed the bot and like kicked us off or something, then that channel would get closed. But until that happens, we just sit there and we wait for those messages. And then we say, well, what kind of message is it? So we use a switch here to say there are different types of messages that we might get. In our case, we're writing a bot that's going to handle certain types of message. We're going to process just messages that are sent to us, just like free-form text. We're going to process messages that send us a location. And we're also going to process messages which are commands. So you can have commands like /alert, we saw, you can have /help, or any command that you want to set up your bot to handle has got the slash on the front of it, and that comes through as a different type of message. So then we say, well, if it's not a command, if it's not a location, here we're just going to take the message itself. So we're setting that to this variable here, t, take that value and just echo it back to the user. So prepare the response and then send it back using this new message call. So pretty simple. Let's actually fire that up and see that in action. So go run, we'll set that going, and then we'll bring up Telegram over here so we can see what's happening. And you can see we've started up the bot and it's okay. So it said, well, you sent me the start command, which we'll show you in a moment. Let's also just say, hello, Utah. And it says, okay, I've got that message from the user, and now we'll just echo it back to them. What you can see here is the response to a command, because we did /start, which is what happens when you initiate the conversation. So the code that handled that, in this case, it says, well, it was a command. So if there's a command, what do we do with it? And we say, well, what kind of command was it? So as a start command, it would be the same if we send it help, and it just says, well, send this sarcastic message back to the user. We can also handle alerts, or we could say, well, if they send a different type of command that we don't recognize, tell them that. So we could say, let's set up an alert. And it says, well, here's the code line for you've set up an alert. And you can say that. And it says, well, I don't recognize that command. And the last bit that we can also handle is locations. So we simply take the location itself, which is a latitude, longitude. We saw that before. And we say, send this location. And it says, well, you sent me a location. So again, I'll go to that branch of the code. So it's actually pretty simple once you've got the boilerplate in place to think, well, how do I want to interact with my users? I'm presumably going to give them some help text when they connect to the bot initially. We saw that when we started the car park one up here. There's that help text there that it provided the user explaining how to interact with it. And then we say, well, if they send us a location, do this. If they send us just a string, do that. Let's have a look now how we get the data in from that API into Kafka. Because once the data is in Kafka, we can use that to drive our actual car park bot, which is going to do things like, here's an alert because a number of spaces became available at a given car park. Here's a lookup against a particular car park. How many spaces are there available right now? So the code for that, I'm going to cancel that bot there. And we're going to head over to here. So what we're going to do first is we're going to get the code, the data from that API into a Kafka topic. Now let me show you where I'm getting all of this information from. Not the information, the example from. This is all on a repository on GitHub called Demo Scene. So I'll post this link to the Slack channel afterwards, and I'll tweet it and all the rest of it. But from here, you've got a bunch of different demos built around Apache Kafka and Confluent Platform. So the one for this is down here, Telegram bot car parks. And all you need to run it is Docker and Docker Compose. And then you say Docker Compose up, and it provisions all of the different pieces. The only bit that you would actually need is the authentication token for a Telegram bot. So you can go and provision that yourself, and then you can actually try this thing out. Because watching someone talk about it and show it is one thing. Actually trying it out and like fiddling with things and changing things, that's how a lot of us really do tend to learn these things thoroughly. So this is the information, and the script itself, the demo script itself, it's on an ASCII doc, so you can just look through this here. And that's what I'm doing when I keep looking up and down between my different screens. Not because I can't remember the demo, but because if I try and type this stuff all in by hand manually, we'll get loads of typos and we'll be here for a lot longer than I have. So what we have down here is the API itself. So it comes from the Northern Data Hub, and it's this particular URL here. And what it gives us is just a dump of some CSV data with a current snapshot of the car park information. So we're going to pull it in using curl, and we'll just echo it to the screen. It says, well, here are your different column headings. Here's the timestamp in local time zone, which is BST, UTC +1, the name of the car park, the capacity, the empty spaces, the status, and so on. And it's just comma separated. And if I run that again, you'll see we probably get the same payload. So 1725 was the last update, 1725. This one updates every 3 minutes or so. So I think we might get a new one. We'll see as it comes through. We'll get a new set of data. And we're basically going to pull that API every 3 minutes and stream the output into a Kafka topic. We're going to do that using a tool called Kafka. And Kafka basically takes each line of input, uses the line separated by default as the delimiter between messages. It takes each line of data and sends it as a message into a Kafka topic. What we don't want in a Kafka topic is that header, because what we've actually got here is a bunch of lines of messages that are going to go into a Kafka topic. So that header there on its own would just be like a string with a bunch of commas that wouldn't mean anything to us in that Kafka topic. So we're going to deal with schemas later on. And that's a really important thing to deal with. But for now, we don't want that in our topic. So we're going to filter it out. We're going to pipe the output of curl through a command called tail, which basically in this case here says start from the second row. So ignore the first row. So now we have that information coming through from that endpoint, and it's just the actual payload of the API. We don't have that header in there. Now we pipe it through again into this tool called Kafka. I'm invoking it using Docker because it means that I don't actually have to have that dependency on my local installation. So it's going to spin up a container, or it's going to use a container called Kafka. and it says, here is my broker, my Kafka broker. Here's the topic to which I'd like to send it. Do it as a producer, -p, -t mimics the behavior of the Linux T command. So as well as processing it, it's going to echo it to stand it out. So we see the same information as before. You'll notice the times increased there. So our snapshot has moved on. And now we've got that information in a Kafka topic. If you don't believe me, and hopefully you do, but maybe you want to see for your own eyes, we can actually just run that Kafka cat command itself. And instead of doing -p, we do -c. So it's going to consume that information from that same broker, from that same topic. And there we've got that data. So you can see here's that data. We've got it from there, and we've got it from here. So different rows of data. This is from when I was running it previously, which makes me realize I probably want to refresh my environment. So I'm going to do Docker compose down, because otherwise the things that I'm going to show you in a moment that we're creating for the first time over, they're not going to work so well because they'll already exist, which will be a bit of a shame. So whilst that's running, I'm going to have a quick look at Slido to see if we've got any questions. We've got some votes in the poll, which is good. People who have tried ksqlDB before but don't think, or haven't tried it before and don't think it's relevant, hopefully you'll find it at least worth a try after you've seen this. Maybe not. Right, any Q&A? We've got no Q&A, so type in the thing on the box, either up there or up there. Any questions that you've got? Can't see any questions in Slack. So that's now spinning up, so we've got a clean environment. So we'll set the data flowing into it in just a moment. I'm going to head over to here and spin that up because we're going to use a tool called ksqlDB in a moment. And ksqlDB, it's an event streaming database that integrates very tightly with Apache Kafka. It uses Kafka for its persistence. So it reads from Kafka topics, it writes to Kafka topics. And as well as being able to process streams of data, it can materialize that data. And that's the real secret sauce to this demo that I've been showing you using the Telegram bot. When we did a lookup to say how many spaces are there available in this car park, it didn't go and read through all those different messages. It consulted its internal state store, its materialized view of the current aggregate across those messages. So demo environment is now back up. Let's go and set some data flowing into it. So I'm going to take the same code that we ran before to echo the data or to pipe the data into a Kafka topic. I'm just going to dump it into a while loop. So this is a super hacky way of provisioning data into a Kafka topic. It's surprisingly effective also. So for kind of like little sandbox environments, little hello world type demos, being able to say I've got something coming out of a standard out elsewhere, let's pipe it into a Kafka topic, is pretty cool. It lets you rapidly develop examples to try out. So we're going to stream that data in. We're actually doing this every 10 seconds just to make sure things feel nice and snappy when we're checking them later on. So we now have data flowing into our Kafka topic. Let's have a look at our Kafka topic and see what we can do with it. Because we still need to get that data, these raw events that are flowing into a Kafka topic, we still need to get that in a form that we can work with it from our Telegram bot that's written in Go. And the secret source in that is ksqlDB. This is ksqlDB. This is the ksqlDB command line interface. ksqlDB itself is just a Java JVM process. It runs separate from your Kafka brokers. It's actually built on top of something called Kafka Streams. So Kafka Streams is part of Apache Kafka, and it lets you do stream processing in your Java applications. ksqlDB is built on top of it, and it lets you do stream processing in any applications because it's got a REST API, which is what we're going to hook into later. But for now, let's just use the command line interface to explore the data that we've got and see what we can do with it. If I say show topics, it shows us the topics. What topics have you got on this Kafka cluster? And I can say I'd like to consume from that topic, print car parks, and it says as new messages arrive, so every 10 seconds, because we're polling that API, whether it's changed or not, every 10 seconds, it's going to get a new dump of data, and so it's going to echo it to the screen. So if I keep talking for another 7 seconds, we'll see in a moment another dump of data come in. It's just consuming from that topic as those messages arrive. But those messages, it's just a string. It's just a comma-separated string. It's a bunch of bytes that happens to have a few commas somewhere in there. And as human beings, we can look at it and say, well, that certainly matches my mental pattern recognition for it's probably a date, and it's sensibly formatted. So I'm pretty sure that's the month. I'm pretty sure that's the day. That certainly looks like a time. Don't know what the time zone is, but it certainly looks like a time. Because I'm local, I know that's the name of the car park. I can guess that that's the capacity because it's more than that figure there. So you can guess at what these fields are. We saw earlier there was the header, which gave us the name for them, and it told us they're separated by commas. But what are the data types? Is it an integer? Is it a double? All that kind of stuff we don't actually know. And when we work with the data, whether we're actually writing SQL to like project those fields against it so we can query it and do analytics, whether we're writing an application, we need to know about those individual fields. When we write an application, we need to be able to say, give me the name where this condition is greater than that. And I'm speaking in terms of SQL, and my background's databases, you've probably guessed that. But if you're writing an application, you need to have the code in your application which says, well, if this value is greater than that value, then do this. And when we say that value, we're talking about a field in the data. So we need a schema. Whether you like it or not, most of the time you need a schema. And people kind of like chose to forget about this inconvenient fact a few years ago and said, we'll just do schema on read. We'll take all of our data and we'll just chuck it around and like CSV and JSON and like we'll do schema on read, which basically means we'll shove the problem down the line to the people who want to use that data. And they said, oh, we'll build like nicely loosely coupled microservices and do all this kind of thing. But by using something without a clear, explicitly defined and stored schema, you actually start introducing coupling back in together because those people writing those applications have to go and speak to those people who are writing the data. So it's much, much better to say if we have data, it should have a schema that's been explicitly declared and registered. Anyway, that's enough, maybe enough about schemas. I'll probably talk about them some more later because they're so important. We're going to create a stream object in ksqlDB. So ksqlDB, it's got a concept of streams and of tables. It says DB in the name, so we're going to have tables in there somewhere. And I'll talk about tables in a moment. But to start off with, we're just going to create a stream. And a stream is a Kafka topic, which is an unbounded series of events, but it has a schema. Here's our schema. It's got a date, it's got a time, it's got these, and they've got data types. It's a varchar, it's a double, and so on. It's defined in this Kafka topic here. So we're saying, take that schema and apply it to this existing Kafka topic. And the data in that topic, it's delimited. We could change the delimiter if it was tab separated or whatever, but by default, it'll be comma separated. So we create the stream. It says I've created the stream. And what that means is we can actually go to that data. I'm going to say, go back to the earliest point in the topic, because side note, Kafka stores data. Kafka persists data, whether you've read it or not. Kafka stores that data until you tell Kafka not to store that data. So when you age it out, you say, I would like to keep the last 10 years worth of data, or the last 10 weeks worth of data, or 10 gigabytes of data, or indeed, I would like to keep that data forever. All of those are completely valid use cases for your data in Kafka. But it means here we can go back in time and replay those messages. So we're going to say select all of these messages from that topic. In this case, we're just going to say show me the first 5. And now here's where our schema comes in. We're projecting those fields. We're not doing what we did up here, which was print out the messages as they come in, just dump those values as they come in to the screen. We're saying down here, select just the date and time, the name, and the empty places from here. This is key. Here are those 4 columns that you asked for. At this particular time here, you can see that's as a result of polling every 10 seconds when the data in the source only changes every 3 minutes. If I take that limit off, you'll probably see that it changes over time, so 1731, 34, and so on. So we've got that source data in the Kafka topic. Every 10 seconds, we're going to get a little on screen as we get another little dump of data from our source ingestion, dumping that data into the topic. Now what we're going to do is we're going to take that source data and we're going to enrich it and transform it. So using ksqlDB, you can do lots of different things with it. I'm going to talk later about building materialized views and stateful aggregations and all that kind of stuff. You can also use ksqlDB for simply cleaning up and transforming source data that you have arriving in a system and getting it into a state, into a target Kafka topic that dependent applications and analytics and so on can read from that cleansed topic. So like transform it once, use it many times. And what we're going to do here is we're going to do a whole bunch of different things. So let me show you. We're going to run another create stream command. But this time we're doing a create stream as select. So this is different from before. Before we did create stream against this topic, and here's the schema. which is kind of like saying register a stream object against an existing topic. This time we're saying create a new stream, which is going to create a new Kafka topic and populate that new stream with the results of this select statement. Because Kafka topics are unbounded, when we query streams in ksqlDB, those queries are continuous because the source is unbounded. We don't know when it stops. That means that the query that we run against it can't just say like, well, I've read up to now, and so I'll just kind of stop, because we don't know if there's more data. There might be data arriving at like 10,000 messages a second. There might be data arriving at 10 million messages a minute, and then nothing for another 23 hours, and then another dump of data. So you get different distributions of data on Kafka topics, but fundamentally these things are unbounded. So we're doing proper stream processing on this. So our select statement is going to say, let's break this down bit by bit. Select star, select everything from our original source stream, which is the one that I queried a moment ago. So bring in all of those source fields. We're going to take that date and time and concatenate it. We're going to tell ksqlDB, well, this is what those different mappings, the time formatting it is. This is the time zone that that data is in. And so we're going to take that and convert it into a proper timestamp field. So it's going to store it as like a big int, the number of milliseconds since the Unix epoch. But we're going to take those two varchar columns, which look like a date and time, but need a human interpretation, and even then it'll probably get it wrong, and say, take that and sort it out once, and now store it as a proper timestamp. We're going to do some calculations against the data. We're going to say, well, we've got the capacity and the empty places, so let's work out the percentage capacity or percentage utilization of that car park at that point in time. So doing stream processing, you can actually start to create these derivations, these pre-calculated fields as that data arrives. We're going to say, let's add in a static field here, which is just going to be useful for data lineage. If time permits later on, I'm going to show you how I can actually add in a second source of data into this same target topic coming from a different API. So you can add in these different fields. We can also modify the schema, and we can map the original latitude and longitude and actually put it into a struct, into a nested field. So here we're creating a struct. We're going to store it as a single field called location, which will have within it the latitude and longitude. In this case, that's really useful because we're going to end up using Elasticsearch for our analytics. And by doing this, we can take that data and have a geopoint within it, which makes the visualizations much easier and much more fancy. The last thing in this set of SQL is we're saying this: create the target stream, serialize the data when you write it to the target topic, serialize it using protobuf. So protobuf, Avro, JSON schema, all extremely good ways to serialize your data on a Kafka topic. Kafka topics just store their data as bytes. Kafka doesn't care how you serialize your data. It just says, give me some bytes. It's up to the producer of that data to say, I'm going to serialize it in this way. So the source data was serialized using a string, which was comma separated. We're going to say, well, that kind of sucks because someone using that data doesn't have any idea what the schema is. They have to guess, which is error prone and rubbish. Instead, we say we've declared that schema. We declared that schema up here when we said, is it going to have it in the history? It is, we declared the schema. We said, this is the schema of that data. And now when we write that data to the target topic, so remember, we've got that select star in there. So bringing in all of those source fields, we're going to serialize that data using protobuf, and the schema itself will get stored in the Confluent schema registry. So now anyone who wants to use that data, whether it's us in subsequent applications and queries, whether it's someone else, a different team or whoever, they can read from that topic and they have access to that schema. Okay, create stream. This time, even though we've got a select statement, we don't get screenfuls of output. We just get saying, yeah, I've created that query. If I say show streams, we can see we've actually created a stream. Here's our source. Against that source Kafka topic, it's delimited, and we just put it into that stream there. We've created a new one called car park events. By default, the topic inherits the name of the stream. We could customize that if we wanted to, and the format is protobuf. If I take that topic there and I say print that topic, it's going to output the contents of that topic. It's going to deserialize it. So let's just pause the output there. It's going to deserialize it and show the value, show the payload. But here we've got the different fields within it. So there's our timestamp stored as the Unix epoch. Here's our latitude, longitude in our struct here. Here's our field that we've added into the source. Here's our derived column, our calculated column. But this is now just a Kafka topic. So anyone can subscribe to that Kafka topic and use that enriched data. So that's the first piece of the main puzzle that we've done. We've taken a source of raw data and we've transformed it, we've enriched it, we've cleansed it, we're reserializing it. And now we can use that for building our application. Okay, let's see how we can build that application. Let's also have a quick pause and look at the questions. So I can see we've got people answering in the polls, and that's good. No questions. So hopefully this is all making like tons of sense, which is great because you don't have any questions. If you have any questions, please do ask. It's great to have some interaction with the audience and not just feel like I'm talking into just a webcam and an empty void. But in the absence of questions, let's carry on. We've got events streaming into a topic. We're polling an API, we're streaming those events into that topic. And those events, let's have a look at the events just for a particular car park, are coming in continually as a stream. So let's say, here's that. We've got a bunch of different events for the same topic, for the same instance of an entity. So here's our car park here called Westgate. We've got a bunch of the same messages. Like I say, because we're polling it every 10 seconds, we get a bit of a distorted view of those messages. But you can see over time, those values change. At the moment, like 5:45 in the evening, I suppose people are starting to drive into town for the evening or leaving work, picking up their cars. So these values change over time. So in our stream of events, things change. But we want to know about what's the current position now. If I go to Westgate Car Park now, how many empty spaces are there now? This is where the concept of materialized views come in, because ksqlDB can actually calculate that stateful aggregation. It can say, as each of these messages come in, I'm going to build I'm going to update an aggregate of those messages. So we can do things like, how many messages have you received? What's the total sum? What's the median value? What's the average value? What's the latest value? And these are all aggregations. So if we had a stream of orders coming in, you could say, what's the sum of all the orders that we've received so far? You can also do aggregations over time. You could say, what's the maximum order value that we've received in the last 30 minutes? So these aggregations are stateful, and as each event comes in, that aggregation updates. And that aggregation is held within ksqlDB, and we can query the state of it. So let's show you how we create the aggregation. We say to ksqlDB, I would like to make sure that you're going to process all of the messages from the beginning of the topic. And then we say we're going to create a new object. Now this time, we're going to create a table. So here's where the DB part of ksqlDB comes in. Streams are an unbounded series of events with a schema. Tables are built on top of Kafka topics, but they hold the state for a key. Each table has a key, and each key has got a value. That value might change. So if we look at what we're doing here, we're saying take the name of the car park, which is going to be our group by field. So that's our key in the table. And then we're saying, look at the average number of empty places. So each time we get a message comes in, it's going to have a number of empty places. So that average is going to vary as each message comes in. So we're calculating that aggregation in a stateful way. We can also use this aggregate here, latest by offset. So simply as each message comes in, based on the offset within the topic, store the latest value. So we're not interested in what the empty places was like 10 messages ago. We want to know what the empty messages is now, which gives us our latest view of that state. So we create that table, and we can say show tables, and it says we've got a table called car park. It's backed by a Kafka topic called car park, serialized into protobuf, and we can now do lookups against that particular table. So let me show you the difference between this. If I say, select these values from car park events, which is our stream for this given car park here, emit changes. This is what's known as a push query. It says, here are all of those events in that topic. And at the bottom of the screen, it says, press Control-C to interrupt, because it's a continuous query. It's just going to keep on running. And as new messages arrive, it's going to push that out to the screen. It's a push query. We've subscribed to that stream of changes. Now let me show you the same thing, but without emit changes. And we're going to query the table. show me the latest timestamp, the number of empty places, the average empty places for this particular car park. And he says, well, here is the average, here is the current number of empty places. That's the latest timestamp of the data that we processed. So this is querying that materialized view. And it doesn't say press Control-C to interrupt. It says this is the answer, and now here you go. It's much more like querying a relational database, which says, well, I hold state, and you query me as a table, and I say, here is the state. And if it's a big table with polar indexes, it might take ages to run, but it will eventually run. It'll say, here is the answer, and we're done. That's what we're doing here with a pull query. A push query, let me show you, emit changes, says, I'm going to show you the current value. And as that value changes, because it might change because events are coming in, they're unbounded, as that value changes, I will give you that value change. I'll echo it out, in this case, to the screen. So a pull query is what's the current state of this aggregate, and we can do that lookup. A push query says, I will tell you when something changes. So with a pull query, this is what we can do. We can actually hook into from an external application using the REST API. So here we're going against the REST API of ksqlDB. We're saying, I would like to run this query here. So select the latest timestamp, the current empty places, average empty spaces for this particular car park where the name is Westgate. There's no emit changes on there. It's just semicolon. Here's my query separator. And it's OK, here is the value. It says you've got a bit of a schema. So here are your schema headers and the data types. Here is your information. This is the latest timestamp. This is the value. And this is done over the REST API. So I'm using curl because I can show you from the bash command line. Here's the latest value. The value has changed. But I can use that from a client language. So there's a Java client which ships with ksqlDB. There are community projects providing a Python and a Go client. So from within your application, you can do lookups against a state store, which is maintained continually with ksqlDB, driven by events flowing into a Kafka topic. And we can do a similar thing with the REST API using push queries. So in this case, we're going to do something a little bit different. We're going to say, set the offset to the latest, so only process new messages as they arrive once we start the query running. And now we're going to say, I would like to know when the car park, this car park here, when we receive an event matching this predicate. So we say where the name is Kirkgate Centre, empty places is greater than 0. So we set that running, and it says press Control-C to interrupt. If a new event arrives on the topic matching that predicate, I will echo it out to the screen. So in that case here, we can see that that condition has been met. So this is a push query. We're subscribing to that event stream based on the matching that predicate. So as events arrive matching that predicate, it echoes it out to here. And we can do the same thing with the REST API. So again, we're going to use curl. So let's clear that down here and here. So again, using curl to do it against the same REST API, but this time we're saying you can pass in, go to the latest offset, emit changes. It's a push query. So to start off with, it says, OK, here is your header. And then it says, here are your new values as they arrive. So if I leave that running, we're going to see in another 10 seconds a new event arrive. It will probably match the predicate. So it will get echoed here to the standard out of curl. But the whole point is you use your client application in Java and Go and Python, and it can pull that directly from ksqlDB. Right, let's have a little look at that Telegram bot itself and see how these things hook in. So there's a question from a participant, are there any other good demo streams to play with? There are a whole ton of really good demo streams. So there's a bunch of good demos on Demo Scene. Quite a lot of those you actually use live data feeds. There's in fact, I'll answer this properly at the end, but there's an article I wrote on like good data sources to use for this kind of thing. Let's see, any other questions? Okay, no other questions. So let's see what this looks like in the context of our Go application. So that's over here, and we're going to open that up in code. So within our application here, and we need our main, we're simply saying we've got the same shell as before, the same kind of like templates that we're using, the same Telegram API. And now we're saying if we receive a command, we're going to handle it in a certain way. So if we receive a command, we're going to say, well, assuming they want to set up an alert, in this case, they said alert, take the argument that they passed us, which we're going to call threshold, and we're going to pass that out to a new Go routine, and it's going to get called within a Go function because we want it to run in a separate thread because it's a push query, so it's actually going to block because it's just going to run continually. So we run it in a separate routine. So we've got this routine called alert spaces, and we can go and have a look at that, which takes the threshold value here, our integer, and it creates a channel which it writes the alerts back to. So as we receive an output from that push query, we write it back to a channel, which then get echoed out to the Telegram bot. And in the background, it's simply running this. So arguably, you could do this just using a straightforward Kafka consumer. You could just subscribe to the Kafka topic, process those messages as they arrive, look for a given threshold, and then write it out here. Here we're doing a different route. We're saying, well, push that logic onto the ksqlDB server. We'll just receive a message when it matches that particular predicate. It uses the community Go ksqlDB client. It sends it out using a push query here. We set the offset that we want to query it from. And so that's how we do the alerting. The other bits that we've got the location one, which works similarly using a push query. And if they send just a location name, then we do a pull query. So this is where we're doing a lookup against that materialized view. So here we say, do a check spaces against the value that they've sent us. So check spaces is the routine. Again, we're using the ksqlDB client. We've got the endpoints and so on built in there. Here's our ksqlDB query. So select these values from car park where it matches the predicate. And then we pass that into a pull query against ksqlDB. We get the results, we check if there's an error, but we get the result back, and you pass those into the variables and pass those back out to the calling routine, which then passes those back in a message which we format and send back out using the Telegram API. So we've taken that same structure of a Telegram bot that I showed you at the beginning, and we've just bolted in saying, well, if they want to do a lookup, we'll add in some ksqlDB code here, which takes the value they sent us, runs the ksqlDB pull query against that ksqlDB server, and returns the value. Let me show you one more thing, because I want to show you some slides in the background to this kind of stuff, because a lot of time the demos are fine, but the devil's in the detail. You want to understand, like, why are we actually doing it this way? Or what on earth are these different components that we're talking about? But the last bit I want to show you is how we can take this data from within ksqlDB. So I'll head back to the ksqlDB command prompt. We've got the data in a Kafka topic. You say show topics, data in the Kafka topic called car park events. We serialized it, we've added in a schema, we've kind of like cleansed this and tidied it up. And then we can say, well, let's take that data and we can stream it somewhere else for analytics. What ksqlDB is not for is random, ad hoc, kind of like big queries. It's definitely not for that. That's what you do in like a relational database, or you do over in like Athena or whatever. You don't do that in ksqlDB. ksqlDB is about stream processing. It's about stateful aggregates, about materialized views that you can query directly on key lookups. But when we're actually doing kind of like analytical crunching, we probably want to take that data that we've transformed and cleansed and push it somewhere else. And to do that, we're going to use Kafka Connect. So Kafka Connect is part of Apache Kafka. And we say we're going to take that data from this particular topic here and push it down to the Elasticsearch sink, which sits at this particular endpoint here. So we've created the connector. Oops, show connectors, make sure it's running, and it says it's running. So that means we can head over into Elasticsearch, which I've got one that I built earlier here. This is actually using that same live feed of data, but with a bit of data that was in existence already. And you can see you can then build a live analytical dashboard on top of that data. You can say, well, how does the occupancy vary over time? That was one of my hypothetical questions at the beginning of this talk. Well, you can see, obviously, overnight, you have more empty spaces because people have gone home. But we can drill into it and understand during the day, how does that particularly vary? We can also use, excuse me, we can also see, using that geopoint field that we created, plotting it onto a map. So we've got data for Bradford. You can say, well, it's based on a heat map of the number of empty spaces. This one over here has got the most empty spaces. This area of town will probably head there first. Obviously, we're not going to call up a dashboard when we're looking for a car park, but it gives you an idea of what you can do with that simple inbound API of some CSV data, once you've got a schema on it, once you've transformed it, built in a geopoint and done those kind of things, it's a matter of just a few commands to then stream it over somewhere else and build a dashboard against it that can refresh continually. So that's the demo. Let me show you some of the slides because I want to make sure that we actually get to these. And then if we have time, I'll show you adding in a separate stream of data. You're all very quiet with no actual questions that I can see. So do use Slack, do use Slido if you want to send in the questions. But now let's have a little look at the slides if I can find the right screen that they're on. And they're over here. So the code itself is on GitHub. I showed you beforehand, but you can go to that QR code, you can go to that short URL and call them up. What we built was this kind of thing, pulling in data from our source API, streaming it into Kafka, from Kafka then streaming it into Elasticsearch, which I showed you briefly then, just using Kafka Connect. No code, just a bit of configuration. And I also showed you how you can write, using Go in this case, a bot which uses the data we've got in Kafka and sends it out to Telegram as the endpoint. So some of the key patterns that I've shown you here are event-driven alerts. You have a stream of data somewhere. You would like to tell your user about when certain conditions arise in that data. In our case, when's there a car park that's got some spaces available for us? But it could be when's an SLA being breached, when is an order being placed. All of these different kind of things are important. It's obviously the wrong time to be coughing, but I do just get a dry throat when I'm doing these kind of talks. So I'll have another little sip of my drink. Another thing that we showed was looking at materialized views that we can query from our applications. So a user wants to know about some given state. We set up that state, that materialized view, within ksqlDB. It's a table because it's value for a given key. And that's maintained as a stateful aggregation within ksqlDB. Our user can then ask questions of that data. The application can query that state that's held within ksqlDB, get the answer back straight away, and pass that back to the user. Also showed how you can take a source data with no actual declared schema, and which is not very useful for applications that want to use that data because they just look at it and it's got a bunch of commas and they have to make a bunch of assumptions or go and speak to the people who wrote that data. Excuse me. And instead, we can say we're going to take that data and we're going to apply a schema to it so that our users can read from a different topic, from the derived topic, which has had the schema actually applied to it. And we do that using ksqlDB. We declare the schema first with our actual DDL saying create a stream against this particular topic. And then we serialize it onto a new topic. And we specify value format equals protobuf, avro, JSON schema. And so the schema itself gets stored in the schema registry. We do a select star from the source stream. So it simply says, take this stream here with our schema. As every event arrives on that source, write it out to the target. But when you write it to the target, write it in protobuf. Also showed you how we can do integration between Kafka and, in this case, an endpoint. But you can do integration both ways with Kafka. You can use Kafka Connect to stream data in from systems upstream. So probably using Kafka Cat to stream data from like standard out from curl is a fairly, it's going to fall over at some point probably. It'll be a bit difficult to maintain and support. Or not, it'll be not resilient, let's put it that way. But using Kafka Connect is a much, much more robust way of actually streaming data in from endpoints, from message queues, from databases, from flat files, from anywhere where you've got source data. So you can take the data from that source and stream it into Kafka topics. You could also stream it from Kafka down to numerous different endpoints. One thing to point out, which I didn't kind of talk about directly, was that data in that car park events topic, that enriched topic that we created, when we were querying it for our source application, it wasn't getting deleted. And I mentioned this earlier, data in Kafka doesn't get deleted when you read it. It gets deleted based on the retention policy that you've set, which is separate from how it gets consumed. So when you consume it in an application, you can use that same data independently and stream it down to an analytics platform or an audit data store or a database or everywhere. So you can consume it independently and send it to multiple different places if you want to. So Kafka Connect lets you build these end-to-end integrations. It's just configuration to set up and use. And it means you can build fancy dashboards like this that are refreshed and maintained in real time from that data arriving in that source topic. But why even build it this way? Like, is this not just overkill? And yes, you could say, I've got an API with curl. Why don't I take that and just put it into a database, into Postgres? And I could query Postgres. And that's fine. It's always possible to take a particular example and say, well, actually, you should have done it this way. But what I want to illustrate in all of this is the power of building it around events. Because events are actually what drive most of the data that we work with day to day. It's just a lot of the time we instantiate it on a database or a NoSQL store. But that doesn't actually tell us about what happened in our business. It gives us an aggregate picture. It's actually events that create what happens around us, or other streams of events. Because these events are so powerful and they enable us to build applications that react to things happening. We can react as something happens in a system, as something happens in our business, because events are not only machine generated, they're human generated. Someone clicks on your website, someone places an order, someone removes some inventory. These are also events. And if we build systems around events, we can actually react to those things happening. We also want to be able to take that stream of events, and this is the power of events, because you can react on like an event by event basis, but you can also use events and replay those events to build up state. You can say, here are all of my order events for today. How much have I sold today? Well, if I calculate all of those different events, that gives me the state, that gives me the total that I've sold. So you can replay those different events. And we also want to be able to provide the latest information to our analytics platforms. So there was a great talk just before this one from Nicholas, and he showed us this idea of being able to do kind of like the ETL and real-time ETL and being able to drive analytics using the latest information, not something which happened an hour ago or a day ago, but as things happen, we can report on them as they happen. So we're working with the latest information when we're making decisions for our business. So to work with all of these events, these streams of events, this is where Kafka comes in. So Kafka is an event streaming platform. Kafka is not just like a fancy message queue or a dumb pipe for getting data between like this place and that place. At the heart of Kafka is the log, but surrounding it is the powerful APIs that we can use. We can use the producer and consumer for getting data in and out. We have Kafka Connect for doing integration between different systems, just using configuration. And we have Kafka Streams for doing stream processing, all as part of Apache Kafka. So within Kafka, we have this log, and the log is distributed, it's immutable, it's append only. So these events which I've been talking conceptually about, conceptually what happens is something happens. So a car park API reports how many spaces there are available, or a network firewall logs an intrusion event, or your application emits an error, or my IoT device emits a thermometer reading, or anything that's an event gets appended to the log. Within that log, consumers can then seek back and forth and read from the beginning of it, or just read new events as they arrive within it, or seek to any particular point and scan through from there. The data is not deleted as it's read. So one consuming application can be processing that data. Another consuming application can completely independently also be reading that data. And you can also add in consumers at a later date, which means that you collect these events. So as something happens in your business, you write it into a Kafka topic. You've got your initial use case application, which is reading those events. You've got a second one that comes along later, or some analytics that you want to add in. And then a month later, someone says, oh, you're collecting car park information. That's really useful. I'm going to build a new application that can take advantage of that same data. So using Kafka as your platform gives you the real ability to evolve flexibly as new applications and requirements come along. With ksqlDB, it acts as a consumer and producer for data in Kafka. We saw how you can read from a topic, transform it and write it back to a new topic. You can consume that topic again and daisy chain your transformations as you need to. You can also take that transformed data and push it downstream for analytics, or use it to drive applications. So in this case, driving application was if there's a space that becomes available, send a message to the user. It's an event-driven notification. But ksqlDB also gives you the ability to build these materialized views, which our applications can query directly. And you say, what's the current balance for this given account? And ksqlDB is maintaining that within its system. So it gives the answer back straight away. Within ksqlDB, like I say, it's just a producer and consumer. It runs as a JVM. It's built on top of Kafka Streams. It uses RocksDB for its state store. And you can actually run it wherever you'd like to. I'm running it on Docker on my laptop. You can run it on bare metal, on Kubernetes. You can also have it available as a managed service on Confluent Cloud, which also gives you managed Kafka Connect. But there's plenty of places you can run it if you want to just yourself on premises or yourself on the cloud. So Kafka itself gives us these key characteristics, which you might say, well, actually, you could have built it a different way. But if you take a holistic view of how we build systems and how historically we've ended up in a right old tangled mess from all these point-to-point tight couplings, Kafka lets you take a step back from that and take a much more broad view over how we actually build things. It lets you take advantage of streams of events. Say, as something happens in my business, I'm going to store that event. I can subscribe to that event and consume it in real time. I can do things with that. I can process it. I can transform it. I can also build stateful aggregations against it. The data is stored in Kafka based on your defined retention policy, so multiple applications can use it. You can also build integrations between systems into Kafka and out of Kafka. So this is what Apache Kafka gives us. So I showed you today how you can build event-driven alerts, how you can build applications that do key value lookups directly against ksqlDB powered by Apache Kafka, how we can also do integrations with this idea of streaming ETL out to target systems. So hopefully that's been interesting. I'll do some questions in a moment if you have any. I'd like to share a few resources with you. The first one is the demo itself. Scan the code, go to the URL, go and try it out. Docker Compose up, and then you can actually go into the ksqlDB CLI and actually try out these things. What does a create stream actually do? Can I do this thing against it? And lots of time you can. It's very, very capable. Go and sign up for Confluent Cloud. You've got a managed Kafka Connect. You've got managed ksqlDB. You've got a bunch of discount codes there that you can use to get money off your bill. So go and sign up and give that a try. And when you've signed up for your Confluent Cloud account, or you've got Docker and you're doing this all locally, head along to developer.confluent.io. And on there, you'll find loads of tutorials, of podcasts, of webinars, of all sorts of content to really get you started on your Kafka learning journey. So with that, thank you very much for your time. I think I've got a couple of minutes spare, so I'll go and have a quick look at Slack now and see if we have any more questions. But if not, thank you very much for your time, everyone, and enjoy the rest of the conference. I can't see, okay, in ksqlDB, is the data persisted to disk as a physical table, or is the data returned dynamically from memory against a schema? So the data in ksqlDB is physically persisted in a Kafka topic. So whether we're consuming from a Kafka topic or whether we're writing to a new Kafka topic based on the results of a create stream or create table as select, we're writing to a new topic. So I think the answer is somewhere in between. So the data is persisted on disk as a Kafka topic, and it's returned based on the schema that you provided. If you're using a table with stateful aggregations within it, then a lot of that happens in memory. I don't know the details of it. There's some great details on the Confluent blog where the ksqlDB engineering team have kind of like gone into the guts of it. But there is definitely memory components involved there. But I don't want to overpromise or over-explain on something I don't understand in enough depth. So confluent.io/blog, there's a bunch of great stuff there. There's also a Slack community. Let's see if I've got a slide to share that with you. There's some free books, they're good. Go along to that Confluent community, cnfl.io/Slack, hashtag ksqlDB channel. There's a bunch of really, really helpful people on there who can answer that question in detail. Another question, as Workbench is to MySQL, is there a GUI to build and integrate objects rather than using command line? Yes, there is. So I'm a command line person. That's why I always show a command line in my demos. There is Confluent Control Center, if you're doing this kind of thing, self-hosted. There is also Confluent Cloud, which has got a web user interface. Both of those, Confluent Control Center, Confluent Cloud, give you the ability to examine your streams, it's got an editor built in. It's also got really cool data flow visualization. Stay tuned to the Confluent blog, because I've got a blog coming out soon, which actually shows all of that web interface as well. So stay tuned to that. Send me a message on Twitter. I'll send you some screenshots as well if you're interested. With that, I am out of time, so I'll finish there. I don't want to overrun into someone else's session, but thank you very much, everyone, for coming along. Follow me on Twitter, and I'll stick around on Slack now if anyone has any more questions. Thank you very much.
Thank you so much, Robin.